Thanks for coming out today to talk about some basic physics and some very interesting phenomena in that area. My name's George Musser. I'm a contributing editor at Scientific American magazine. I was before the senior editor for space science and fundamental physics at that magazine for, I guess it was something like 15 years. Actually, you have an undergraduate degree in EE in math, and the very first program I wrote was not Hello World. It was actually in machine language using actually hexadecimal. I was like 10 years old. This is back 1980 or so. And I made an LED blink. I was so proud of myself. Today, you can do that in 2 seconds on an Arduino or whatever. My graduate work was on the planet Venus. So if you have any questions about Venus and you're willing to put up with information that's 20 years old, I'm happy to oblige you in the Q&A session. So the phenomenon I'd like to get at today is called non-locality, or as the title suggests, spooky action at a distance. That's the somewhat derogatory appellation that Einstein gave to this phenomenon back in the 1940s, actually. So before I get into some concrete physics about it, I kind of wanted to spiral in on the topic and give you some just general remarks about it, and then we'll get progressively more specific over the course of the talk. The basic idea of non-locality is you can have a connection between different things. Something here can be connected to something over there. And the nature of the connection can vary, but in some way or other, the fates of those objects are bound together. In a sense, to touch one is to touch the other. You can have an effect from propagating from one to the other. And obviously, physics, the physical sciences in general, is a story of connections in the world. That's what physics tries to do. But what's unusual about this particular type of connection is there doesn't seem to be a connector. There's no rope, there's no handcuffs binding the two things together. There's none of the standard mechanisms of physics like forces, waves, intermediary particles. These things are acting on each other at a distance, hence the name of the phenomenon, or phenomena, actually. As we'll see, this is a variety of phenomena. And the question is, what is up with that? Like, what could be explaining this weird connection without connector? So, spiral in a little bit more, get a little bit more detailed. Usually in the laboratory, the objects that are being connected are subatomic particles. They don't have to be, by the way. That's just, particles are easy to manipulate, and the principles that govern them are quite pure. They're not confounded by the complexity of the system, for example. But in principle, you could take these two bottles and connect them. I mean, anything can be connected through this process. So what you do is you might create the particles at the same time through the same kind of process, so they are connected by virtue of a common origin. Or you might have them already created, bring them together, bang them together, interact in some way, and they develop this peculiar connection whose nature I'll elaborate on. And typically in these experiments, you might hold on to one, there may be two of them, you might hold on to one of them, and you give the other to your friend, who then goes off to the other side of the laboratory, or the city, or the solar system, or the galactic empire, or wherever they may go with their own individual particle. You then manipulate your particle in some way. You measure it, really. It gives some kind of response. Your friend does the same to her own particle, and it gives some response. And they're the same response. That's the nature of this non-locality. The particles are remaining connected without a connector. They remain coordinated without any kind of seeming, at least, that there's no kind of mechanism to coordinate them. So this is, if you had to give something as close to Harry Potter as you can imagine, this is really it, at least in contemporary science. This is the closest we've got to magic. A very subtle form of magic, as I'll come back to later. It's not the kind of thing you could use to apparate or levitate things or transmute them or whatever. By the word magical, it just means that it's not explicable in our current physical framework, and our current theories don't seem to have an explanation for it. Now, this synchronicity between these distant particles, these distant events of measurement of particles, is something Einstein was greatly troubled by. It goes back to the very, very earliest days of quantum mechanics, actually just over a century ago now. And he was actually much more worried about it than almost any other aspect of quantum theory. And people talk a lot about God not playing dice with the universe, and Einstein was very worried about the indeterminism or randomness of quantum theory. But non-locality is actually above that in his list of problems with the theory, or conundrums with the theory. It's actually the only thing he ever wrote a paper about, which indicates the level of concern that he had, whereas randomness was just something he kind of complained about to his friends over dinner. Now, if I had been giving this talk 10 years ago, let's say, I would actually be done now. I could take your questions. Because that's kind of as far as people could get. They knew there was a mystery. There actually were technological applications for it. But there was no understanding in any kind of detail. There's no explanation of it. And the job of physics is really to naturalize the supernatural, is to domesticate magic and kind of pull it into the realm of rational explanation. And my book is kind of a meager attempt to do that, to give a naturalistic explanation for what seems on the face of it supernatural, this non-locality. And that explanation will come, as I'll elaborate on, in the form of a failure of space, space-time more generally, but I really focus on space, this concept of space, which in any kind of basic physics is taken as the substrate, is taken as the fundamental stage on which the world takes place. And everything's phrased in terms of space, the x, y, z, and a t if you have time in there, coordinates, distances, sizes, everything we talk about in physics is spatial in some way or other. And non-locality seems to be undermining that. Seems to be suggesting perhaps there's a deeper level that underlies space. At least that's the proposition that I'll put forward today. That deeper level might indicate a need for a unified theory of physics. So it's essential to that whole quest for unified theory. It might actually kind of already be in our theories. We don't really need to unify them, but it's there, not fully appreciated. So there's different ways, but in some way or other, you need something to underlie, at least in this way of thinking, to underlie space. So let me, again, continuing my tour of the subject, spiraling in on it, let me dissect the idea of non-locality. And to do that, I need to tell you what locality is. What am I negating? What's the non in front of? And the word locality has, in physics and philosophy, different associated meanings. It's really kind of synonymous actually with spatial. When you see the word locality, you can almost kind of substitute in your head spatial. The two ideas are closely related, but locality is a bit more specific about what it means to be spatial. It has different meanings. So meaning number one is things have locations. Physical things, at least, exist in places. They have a quality of having a quality of being localized to a place. If you can't point to something, in a physical thing at least, and say, here it is, it doesn't really exist in a sense. Well, teacher wants to know where your homework is. I don't know where it is, nowhere. It's tantamount to saying it doesn't exist. Second, a second important meaning is that things in different places are different things. They have an autonomy. They have an autonomous existence to them. That's actually what we mean by thing. I mean, what does the word thing really mean? It means a localized part of the universe, a little piece that you can kind of carve out and say, there's an identifiable thing. It has an existence that's independent of the other things that the world consists of. Third, and this is the one that kind of people focus on in terms of the theory, things in different places, so hence different things, are isolated from one another. They have a measure of isolation. They, of course, interact with one another, but they always interact through the space that separates them. So they might interact by actually moving through the space that separates them and banging into each other, called contact action. That's kind of the original sense of locality, going back to the ancient Greeks. Contact action, where atoms would come together and hit. But in modern physics, we also have waves, we have intermediary particles, other ways for them to interact, but it's always through space. Now, the need to interact through space tells you actually a lot just on its own. It's kind of very basic, almost metaphysical concept. It tells you, for instance, that the interactions between objects is attenuated by the distance between them. So if I double the distance between them in a lot of force laws, it's a 1 over r squared relationship. It goes down by a factor of 4. Sometimes it's actually not such a simple force law like with springs, but in some way or other, increasing the distance between objects makes it more difficult for them to interact. It introduces a time lag between them because things have to have time to get from one to the other, and that is limited by the speed of light in our current theories. That's really the role the speed of light plays. It's actually not the speed of light. That just was a historical thing. It's the speed of the maximal speed of interaction between objects in the universe. So this idea of non-locality and spatiality is really fundamental to our entire intellectual framework. It's not just about physics. It's all the natural sciences. And it goes all the way back to the sources of natural philosophy in the ancient world. Ancient China and ancient Greece both articulated in different ways a principle of locality. And I mean, you think about it. What does science do? What is the purpose of basic science, at least? It's to create narratives of the world. Things exist at certain places. They move around. They interact. And you can break down in theory, you can break down any process into that kind of step-by-step causal narrative. And that is dependent on the fact that we have this idea of locality. It also has a methodological importance. So the world is so big and I am so small, I can't possibly comprehend the entire universe. What do? I break it down. I look at this piece, I look at this piece, I look at this other piece, I see how they interact. That's usually the hard part. And I can do that because the world is divisible into pieces. The world lets us understand it. That's actually extremely profound, and we're lucky that that's the case. Probably we couldn't even exist if that weren't the case. We certainly couldn't exist as rational beings unless the universe were explicable in some way. And that's something Einstein also commented on. And finally, just let me throw up one of the many philosophical implications of locality, and it has to do with our personal identity. So what does it mean to be an individual? Well, it means that each of us kind of has our own integrity. We occupy a certain position, a little volume of the universe, and that ultimately is underpinned and guaranteed by the principle of locality. Because anything that affects me has to pass through the space to get to me. It has to actually pass through my skin or enter me somehow. And if that weren't the case, if things could just reach out, if somebody could reach into your mind and control your thoughts, well, you'd begin to question whether your thoughts were your own. Your whole sense of personhood would be violated. So your sense of personhood depends on this concept of locality as well. So I just bring all this up really as a way to demonstrate the mystery, the depth of the mystery that non-locality is going to represent. And God knows physics talks about lots of weird things. We've got dark energy, matter, any number of things from quantum physics. I mean, just name it. Even turbulence. I mean, so many things in the world are just plain weird. That's the fun of the world. Thank God it's weird. Otherwise, like, why are we here? But locality is a weirder. It's the weirdness. It's the thing that kind of burrows into the very foundations of science and makes us question the whole enterprise. Okay. On the one hand, just to sum up quickly, the world has this quality of locality. Things have positions. They interact in space. We're individuals. Science can partition the world. And so locality does seem to be an important characteristic of at least the observable world, the world that we inhabit kind of in a daily life. But if you look more closely or do special analysis of our current theories, you see this non-locality. And it comes out in different ways. I'll discuss a couple of the ways today, but let me just kind of survey a few of the different ones. And what's interesting is actually there are many different ones. It's not just the one Einstein originally worried about subatomic particles. There's also a lot of different kinds of locality having to do with black holes. That goes back to the work really of Stephen Hawking. And you're probably all aware of this impending announcement, one hopes, at least the rumors are right, about gravitational waves. And the importance of that announcement probably ultimately is that it will tell us a lot about black holes. So black holes are going to be in the news a lot in the coming weeks, at least if the rumors are correct. The workings of gravity also have a subtle form of non-locality in them, which is ironic because Einstein invented his theory of gravity, general relativity, to banish the Newtonian non-locality that had been there. I can come back to that later. But this is something that was really only appreciated in the 1990s. Cosmology, early universe observations, Big Bang, all that. There seems to be, although it's more controversial, some kind of non-locality there as well. That's kind of weird. So in these different ways, you get different violations of those principles I mentioned earlier of locality. So one example is in some of these forms of non-locality, the things at different places are not isolated from one another. You can actually affect this one and boom, instantaneously affect the other one over there. The effect jumps across it as if going through hyperspace or something. More subtly, the world can have holistic qualities. So what that means is, and this is kind of a difficult concept to wrap around. I mean, we use the word holism if you go to yoga class or whatever, but this is a more kind of subtle form of a holism, and I'll come back to it a few times in the course of the talk and try to zero in on it. So you don't get it the first time, that's cool. The idea is that properties cannot be attributed to the parts of a system. They're properties of the collective of the system. And that's a type of non-locality. You can't localize the property to any of the pieces. In fact, it's worse. You can't even build up the property from the pieces. It's not like a Lego set where you get a house from lots of little bricks. There's certain properties of the whole that actually cannot be partitioned in that way. And that's a type of non-locality. Now, this is something that you learn as a really, it's probably actually going probably into high school physics, but certainly undergraduate physics, graduate school physics, a lot of these concepts are brought up. But what got me personally interested to the level that I would write a book about it is that I saw connections among these different areas. So I kind of try to synthesize the types of non-locality in these different areas. And the fact that you have a lot of types is interesting. It indicates that this is just not an isolated curiosity that you can kind of dismiss and put in the carnival sideshow or whatever. It's actually something that is maybe at the root of the mysteries that we face in physics today. Now, I'm going to throw out a general purpose disclaimer before I get into some of the concrete cases. I have to do that for scientific honesty. A lot of people, scientists, physicists, doubt a lot of these intimations of non-locality. They think maybe it's a misinterpretation of the theory or of the experiment. And there's actually quite an interesting and vociferous debate over that, which I do talk about a little in the book, trying to pick it apart. And you can see where those skeptics are coming from. I mean, locality is a very successful principle. It's something we observe just from our senses, so why question it? But this is one of those cases where I think the evidence is strong enough. You don't have to make a stronger case than that. It's good enough that we should pursue what it means. And that's what I will do the rest of the talk. So disclaimer over. So let me go into a couple concrete cases of this non-locality. And I'll start with the one that concerned Einstein, quantum entanglement. Often when I give these talks, people get hung up on the word entanglement. And you really just think about it as a romantic entanglement kind of thing. It's a relationship between objects, a connection between them that's kind of awkward, actually. So this particular laboratory is in upstate New York, Colgate University. And if you've ever been in a physics lab, it's actually kind of typical. There's a coffee maker kind of on the left here, which is an important and essential part of any laboratory. It's the laboratory of Enrique Galvez, who is a Peruvian, actually I think he's a naturalized US citizen now, who's really been a pioneer in miniaturizing these experiments. These experiments actually this particular kind of experiment goes really back to the 70s or even the late 60s. But they were humongous, taking up the whole lab kind of experiments. And now you can really pull it down onto, this is the size of a dining room table. You can actually get it probably under the size of this podium. That's kind of the progress of miniaturization on this. So one thing that's kind of cool about this table, by the way, is you see those little holes on it. Those are, it's like a pegboard. You can actually screw the components down. And that's super important for getting the alignment in these experiments correct. That's the hard part about doing these experiments is they spend, months of well, Colgate's an undergraduate institution. Poor RA is coming in to try to align these mirrors and things. So this particular version of the experiment uses light. It's an optical experiment. It uses photons, in other words, photons, particles of light. And photons are great because they're easy to manipulate. There's also just an established technology for manipulating them. So there's mirrors, filters, prisms, nonlinear crystals, optical fibers, the whole range of equipment that's available for these experiments. Photons also have a lot of different properties that are nice. Obviously, they have color, so energy, momentum, the direction they're moving in. But the property that's usually focused on is their polarization. Polarization's, it's a binary property, so it's just easier to deal with. The others are reals, so it's kind of harder to deal with a continuum quantity. Hard part about photons is detecting them. Remember, you have to detect these photons particle by particle. So there's a lot of confounding light in these experiments. It has to, when this room has to be completely darkened for them to do the experiment. Even all the LEDs and everything we have is LEDs in it has to be taped over with electrical tape. There's a big curtain drawn around it. It's actually kind of spooky just by the virtue of the setup when they do it. Other kinds of particles have countervailing trade-offs. So maybe they're easier to detect, but harder to manipulate, like electrons, protons, charged particles. And I don't know if anyone saw, there's a big New York Times article in, I guess, beginning of November, maybe late October. Spooky action at a distance proved something. That was the headline, something like that. And what was cool about the experiments described in that article is they kind of combined the advantages of different types of particles. So they used photons to kind of connect different parts, wings of the experiment, but electrons in the wings of the experiment because they were easier to detect. So there was kind of a hybrid approach that kind of got over a lot of the difficulties of doing this experiment. But this particular photograph dates to, I think, 2011, so it kind of predates that. So from this angle, this is kind of a blurry shot, but I show it because you can see kind of two, if you run your eye, I should have drawn a line on this. If you run your eye vertically on this, you see two like lines of instruments. And those would be the two entangled photons in this experiment. So let me just show you the kind of schematic of this. So it starts when you have a laser in back that emits a stream of photons. And they're blue for a purpose. They actually are blue or maybe near ultraviolet photons. And they run through different kind of setup instruments that align the beams and clean up the beam and everything. And then they hit the thing I call a crystal, and I'll come back to. And that splits them through a nonlinear process into two photons, each of half the energy. So that puts it into the red part of the spectrum. And then they hit, because I'm dealing with polarization here, polarizing filters. And they either get through the filter or not. And then they're picked up by a detector. Actually, they go into a set of fiber optics, and they're picked up by a detector and an instrumentation at the bottom there. And they look for coincidences. So when the photons kind of hit the detectors at the same time, whether within the same certain window, that counts as a coincident detection. These particular detectors, by the way, are about 10% efficient. So 1 in 10 photons that strikes them gets picked up. And so 1 in 100 pairs that strikes them. That kind of statistics becomes important, but has been overcome in these recent experiments. So this is my finger pointing to the polarizing filters, because that's a central element of this experiment. It gives you a sense of scale. That's the distance over which, in this experiment, the spooky action is occurring. So it's about the width of my palm or hand or whatever. That's the spooky action distance in this particular experiment. But that can be extended to arbitrary lengths if you want to. But here we just do it to that width. These things look like 35 millimeter camera lenses, like a 50 millimeter lens. You can turn the dial on the side, and that changes the orientation of the polarization of the filter. So in the past, I've given a talk very similar to this. And at the end, and an email afterwards, everyone always asks me about that crystal I mentioned. The crystal that splits the incoming blues into two outgoing reds. And I think it's a crystal. Sounds kind of weird. But it's actually, I didn't even get into the details in it in previous talks and not even in the book, because the details actually don't matter. But to head off any questions, let me go into the crystal for a couple minutes, because it is actually kind of cool physics. There actually is an amount, that little transparent cube in the middle is actually an example of this crystal. It's actually a crystal with barium borate. Barium borate comes in different crystalline forms. This is the beta phase of it. And it, as this kind of cool image shows, it actually splits the incoming beam into two outgoing beams through this process known as down conversion. Spontaneous parametric down conversion is the full title. And each of those terms has a meaning, but down conversion. This actually, picture, by the way, is really hard to make. This is a long exposure. It's probably a composite image even. And they actually made it by taking a piece of tissue paper and running it along the beam during the duration of the exposure so you could actually see it. Because otherwise, you don't see the beam in the laboratory. It would be bad if you did, because that means there'd be scattering from the beam and you'd be reducing your intensity of the beam. So you don't want to see the beam usually, but in this case, for the dramatic picture, they did that using a little piece of paper. It's actually kind of cool. So the splitting that occurs in the crystal, the very center of this picture, is, you can kind of loosely think of it as a type of refraction. It's a nonlinear, kind of exotic type of refraction. That's kind of what's occurring here. It actually requires quantum field theory to explain fully. But just for simple purposes, think of it that the beam is actually being refracted into two outgoing beams. Now here's kind of a schematic diagram of that setup. There's a crystal, that's that kind of block in the middle. And that white line, if you can see it on the side of the block, that's the optic axis of the crystal. So what you do is the crystal is symmetrical about that axis. You send in in this case, vertically polarized light parallel to that axis, and the crystal will create two outgoing, horizontally polarized photons. In this case, the photons had the same polarization, namely in the horizontal direction. Now, in case you ever watch a YouTube video or look this up, I think even on Wikipedia or certainly in any magazine articles, often they describe a setup where they're opposite polarizations, and there's no contradiction there. The setup, you can actually set up the crystal to do both. But in this experiment that I'm describing, they're the same polarization. So you can rotate the whole thing, just do whole thing 90 degrees. Again, you send something photons are polarized parallel to that axis, and they come out polarized perpendicular to the axis. So that is how you get two photons. Now you need two entangled photons, and that's something a little bit more subtle. So if you don't get it the first time around, I'm going to come back to it later, but let me spell it out, and then we can talk about it if this doesn't make any sense. So what does it mean to be entangled? It means that the photons have a polarization, that the pair of photons has a polarization, but the individuals don't, which is to say the individuals have an ambiguous polarization. That goes back to this whole business of the property can't be localized. So each photon, as I'll show in an animation in a second, actually doesn't even have a polarization, but the system as a whole has the property of they're the same polarization. And that's the mystery here that we're trying to solve. So the way that's done in the experiment is you take two of those crystals, you pair them up, you send in diagonally polarized light, and it comes out with an ambiguous polarization. It's the same polarization on both sides, but it's an ambiguous polarization. That's the weird thing about entanglement. The ambiguity is only resolved later when those things actually hit a detector. When they hit a detector, they resolve, and they're, in this case, either horizontally or vertically polarized, but they're always the same each time. And I'll come back to that in a second. So crystal is nice because it gives you a controlled way to produce entangled photons. But I want to emphasize that there's nothing special about the crystal per se. It's not like a metaphysical crystal that you buy in a Haight-Ashbury kind of thing. No, it's just a particular good way of doing it. I don't know if any of these lights in here are fluorescent. They look LEDs to me, and spots probably aren't. But if you go into the fluorescent lights in the hallway, they are emitting entangled photons. This is something that's not actually widely known. The very first experiments, in the 1970s, actually used mercury vapor lamps, because a mercury atom gets excited, and then it decays from its excited state by emitting photons. It sometimes emits photons in pairs, and those two pairs will be entangled, will spin entangled, or polarization entangled with one another. I did a version, like a do-it-yourself version of this experiment in my basement using a radioactive isotope, sodium-22. It gives off entangled gamma rays, and they can be picked up by a Geiger counter. A Geiger counter is just an extremely cheap photon detector, basically. So you can do this with all sorts of different ways. You can just bang particles together and entangle them. So there's nothing special about a crystal. It just gives you a controlled way to do this experiment. Now, the physical implementation of this isn't important. So we can go to a higher level of abstraction. We don't have to work at the physical layer here. We can go to a higher level. You can think of these things as coins. That's the higher level of abstraction. We can take this. Each photon is kind of like a coin, like flipping a coin. The whole thing is an extremely expensive coin tosser, like $10,000 coin tosser. And what it does is it creates coins, flips them, creates another pair, flips it, creates a third, flips it, thousands of times a second, adds up the statistics. So whether it comes up heads or tails is whether it goes through the polarizing filter or not. And those things are dialed, so there's a 50-50 chance it's a fair coin. So you can go to this higher level of abstraction, and a coin gives you a certain series of results, heads, tails, et cetera, purely at random, unpredictable by the indeterminacy of quantum mechanics. Go to the other side, you also get heads, tails, blah, blah, blah. Again, completely random, completely unpredictable, indeterminate. Both sides, they're the same outcome. That's, in this particular experiment, that's the connection we're talking about. That's the weirdness that is at the heart of this entanglement experiment. Two random outcomes in two places giving the same result. They're like two coins being flipped on two different football fields, all giving the same answer. I like the coin metaphor. for a number of reasons. Obviously, any metaphor will have its limitations, but this one does get across the idea that these are two independent events, two independent coin tosses coming out the same on both sides. That's the kind of ambiguity I was talking about earlier. Before you flip a coin, almost by definition, there's no outcome to it. It's ambiguous. Otherwise, why flip? So unfortunately, a lot of my Amazon reviewers are missing this particular point and bringing me down in their stars because they're saying, well, George, come on, what's the mystery here? Why did you write hundreds of pages on this topic when it's obvious? You've created identical coins, and you toss them, and they give identical outcomes. It doesn't seem mysterious at all. Well, that's partly an artifact of this particular setup of the experiment. It's also kind of a misunderstanding that quantum theory is indeterminate. So these are indeterminate tosses coming out the same. But to prove the point, what you can do is you can do an elaboration on the experiment. I can dial those polarizing filters to different settings. I have complete freedom. I can dial that actually at any setting I want. But I'll choose two particular settings. So there's 4 permutations of settings on the left and the right. And I'll just, for the purposes of metaphor, say that's like flipping the coin with my left hand or with my right hand. So I choose the hand at random. In other words, I dial the polarization at random. So what I've designated left comes out whatever. I go down the line. It's a series of outcomes. And so there's 2 levels of randomness here that's important. One is the choice of hand with which I'm tossing. And if I'm coordinated, which actually I'm not, I can flip them and get these kinds of results with either hand. And there's the randomness of the outcomes. I can do that on the other side as well. And I get actually a different series of hands and in general and a set of outcomes. So in this case, they're not exactly identical. This is where we start getting to some of the mysteries of it. You notice that I've highlighted them 2 exceptions to the identical rule. They're not identical on both sides. They're identical for 3 of the 4 permutations of left and right hand, but for one, they're actually always anti-correlated, always the opposite outcome on the 2 sides. Now notice where you get the exceptions. You get the exceptions only if and only if coin 1 is tossed by the person with their left, and coin 2 is tossed by the person with their right hand. In all other cases, you get a different outcome. So the outcome depends on both sides inextricably. It's as though there's a communication between the both sides. That's the kind of connection I'm talking about here. And you can elaborate on this to your heart's content. There's just a zillion different ways of polarizer settings. You can do 3 particles, 4 particles, infinite number of particles in principle. And you get outcomes that cannot be explained simply by taking 2 identical coins and flipping them. It's more subtle, obviously. No known force is acting to interlink the 2 sides and communicate between them. You say, known force. Well, what about unknown forces? And that's always a concern because we certainly don't think our theories of nature exhaust the possibilities out there. Probably the Higgs boson comes with a whole series of Higgs-like forces. Maybe they could communicate, who knows? But you can rule that out. One easy way to do it is just move the particles further apart and see what happens to the correlation between them. And it's not affected by that. So normally if you have 2 things that are correlated, say, by a wave, and you double the distance, you expect the strength of the correlation to diminish, and that doesn't happen here. So there doesn't seem to be anything passing through space, no force, even an unknown kind. But also what's done here is the experiment is done too quickly for a force or a hypothetical effect to propagate. You actually do it at the exact same time. You measure this particle and change its setting at the exact same time as you do it over here. So any force would have to be instantaneous across that distance. It would have to move infinitely fast. Infinitely is obviously faster than light, so that is ruled out by Einstein's theory, or at least would contradict Einstein's theory in a very serious way. So it doesn't seem to be caused even by an unknown force. We're left with this magic, this weird thing. I promised to kind of qualify that word magic a little bit, and I'll do so now. The magic is extremely subtle. You're not going to win a Wizarding Cup with this magic. You're not going to even pass your owls with this magic. Because you don't see it if you just confine your attention to one side or the other. You just see heads, tails, whatever. Other side, heads, tails. You just see 50-50 outcome. There's no statistical variation on the 2 sides. Only when you compare them do you see a pattern of any sort. So very subtle, very weak form of magic, but it's still pretty weird. By the way, that's the reason, and I have to say this whenever I'm in California doing this, no psychic powers can be involved here, no telepathy. This is not going to be of any use to explain paranormal phenomena, even if those phenomena could be verified experimentally. Actually, in the 70s, that was a live issue, so it's been settled. Still pretty cool, though. There's lots of technological applications, obviously, for quantum computers. Or certain types of quantum computers, this is important. The one that gets the most traction and the most attention is cryptography. You can use this to certify the privacy of a communication channel. And essentially, the way it works is you keep one of the particles that are entangled. You give one, or send the one across to the person you're communicating with. And if the NSA intercepts it in the middle, it will change the correlations that your friend receives on the other side. And there's no way for even the government to mimic that connection. It's just guaranteed by the laws of quantum physics. And then once you've established that communication channel, you can send a secure key from one party to the other, and then encrypt whatever message that you have. OK, so that is quantum entanglement. Just to give you a flavor of how broad the concept of non-locality is, and then I'll try to get into an explanation for it. I'm going to mention at least one of the types of non-locality that are involved with black holes. And again, we're going to be hearing a lot about black holes in the coming days, so that's kind of cool. Here is a picture of a black hole indicated by that arrow. Not much there, and which is kind of the point of it. You do actually see a little bit of gas at where that arrow terminates. And this is an infrared image. And the spectrum indicates that the gas has a temperature of 10,000 kelvins. Now, if you had a region of that size glowing with the temperature that's much hotter than the surface of the sun, you would have kind of a little star there. In fact, what you would see is something more like that. So there's a disconnect here between the temperature that's observed and the luminosity of the object. The object is way under luminous. The energy is going missing. It's going down the black hole. That's some of the best evidence we currently have for black holes. This kind of missing energy, and also speaks to what is a black hole. It sucks things in, can't get back out. So this is from the movie Interstellar. Then some of the simulations of gravitational lensing done for that movie. Black hole basically looks like, from the outside, a giant, extremely dark planet with a lot of stuff around it, usually. And if you fall into it, there's no hope for you. You just fall in, and that's it. You're dead. So what's important here is the irreversibility of the act of falling in. You can't unfall. You can't ascend out of the black hole, by definition. It's got this perimeter or event horizon that things cannot cross. What's important for our purposes today is that to cross that event horizon, in other words, to escape from the black hole, you would have to exceed the speed of light. You would have, essentially, to violate the principle of locality. The principle of locality is what's really explaining or kind of underpinning the irreversibility of black holes. So there's a connection between irreversibility of black holes, according to Einstein's theory, and the principle of locality. And this is the thing that Stephen Hawking clarified in the mid-1970s. He showed that the black hole is kind of like a big bonfire. It actually incinerates things. So if your hapless astronaut falls in, the black hole will glow that much more strongly, and the energy represented by the astronaut will actually come out in the form of random heat radiation. Now, if you were clever, you might say, aha, I'm going to collect all that heat radiation, and I'm going to turn it back into the black hole, and I'm going to recover my friend. And you would reverse the process, as you could actually do with chemical burning. If I had an actual fire here, God forbid, and were to burn something in it, I could take all the products of that chemical reaction and then run the experiment, in principle, run the reaction backwards. It would be difficult to do, but with an actual fire, but in principle you could. But if you try to do that with a black hole, you try to run it backwards, you just get more of the same. You can't recover your friend. You just get more random radiation. It's actually even uncorrelated with the first random radiation you had. So it's really random now. And no astronaut will pop out. If I were to drop an egg on the floor and it's shattered, a hard-boiled egg, and it's shattered, I can imagine running the whole movie backwards, and an egg would kind of pop up off the floor back onto my plate. You can't do that with black holes. So that is a problem because everything in fundamental physics, the laws of fundamental physics, are all time reversible. If I can move this direction, I can move that direction. If I can make it, I can break it, or vice versa. So black holes seem to be an exception to that rule. Obviously, in daily life, we do see a lot of irreversible processes, but if you look more closely, they're reversible kind of the atomic level. And what gives them their apparent irreversibility is the initial conditions on it, or the kind of asymmetry that you have in there. So fundamental physics is, by its very nature, time reversible. So it looks like black holes are kind of an exception to that rule. So there's something weird going on with them. And you might say, well, it's just black holes and just exotic objects in the center of the galaxy or whatever, so big deal. But it turns out that if you violate irreversibility in any part of the fundamental laws of physics, you would violate it everywhere. It's like being pregnant. You can't be a little bit pregnant. You can't be a little bit irreversible. And so the laws of physics predict, or at least the grounds on which we construct the laws of physics, predict the black holes themselves should be reversible. And I made the point earlier that irreversibility and locality are connected. Ergo, reversibility and non-locality are connected. It's a kind of a subtle argument, but the basic idea is that there has to be a way to get out of the black hole. There has to be an escape hatch in some way, or it had to be exceed the speed of light, or there has to be a tunnel of some sort to get you out of the black hole, all of which would violate locality here. So in the interest of time, I'm actually going to skip the next instance of non-locality in black holes. And if you are curious, ask me about the holographic principle in question session, or just we can talk outside if you like. And it's actually kind of pretty cool. So I promised an attempt to explain these non-local phenomena. So let's think about what the phenomena represent. They connect things like particles or inside and outside of a black hole, pieces of a black hole, different aspects of nature, as though those objects were not separated, as though they actually were just juxtaposed or even coincident. So the thinking is deceptively simple, that the distance between things is somehow a mirage, that things seem to be separated, but they're really juxtaposed at a deeper level. And might that explain the non-local phenomena? So that's just to say that space is a kind of mirage. And mirage isn't maybe the right word here. It's really that space is a construct. Space is built. It's not fundamental. It's built on something. So this is actually where we can make contact with a whole different direction on the problem. And that's always good when you can laterally think like that, having to do with understanding the force of gravity. So in Einstein's theory, general relativity theory, the force of gravity is associated with the structure of space, with in particular the curvature of space. So why does a baseball arc back to the ground? Well, the trajectories through space and time of the ball and the ground will actually intersect. And they'll do that because Earth, its mass, has warped space around it, causing paths that were parallel to actually not to be parallel anymore. So gravity reflects the structure of space-time. And one of the great scientific enterprises of our age is to combine quantum theory with Einstein's theory, to combine quantum theory with gravity theory to give a quantum theory of gravity. Now, this is where you get into string theory, loop quantum gravity theory. You can go watch or read Brian Greene on this, Lee Smolin. I have my actual first book is on these theories as well. And there's a lot, by the way, a lot of controversy and dispute, and everyone hates each other, and it's very vexed. But what's often lost in that debate is they're all kind of saying the same thing in different ways. They're all saying that space, or at least the kind of space that we inhabit, is constructed. It may be constructed by strings. It may be constructed by loops. It may be constructed by cause-event networks. Space may look something like that. So this featureless rectangle is meant to represent the space that we inhabit. It's featureless. I look at space in front of me and I don't even see it. I mean, it has no content to it. But if I were to zoom in, deep down, I would begin to see some kind of filigree structure, quanta of space in some way or other. That might be formed, again, by any of those kind of fundamental ingredients like strings or loops. So again, space is a construct in all these theories, completely independent of all these arguments about spooky action at a distance. This is coming from another tradition in physics altogether. So one thing that's cool about this approach is you can take your intuitions, such as they are, about ordinary atoms, hydrogen, helium, et cetera, ordinary molecules, H2O, whatever, and apply it to space. Some of that intuition should carry over into your understanding of space if both are molecular or quantized in some way. So, water. What are some of the properties of liquid water? So it flows, it can wet things, form droplets, so it's associated with surface tension. I can send waves through it, sound waves or ripples on the surface. I could freeze it, boil it. In other words, I could change its state. All those properties of liquid water are not properties of H2O molecules. H2O molecules don't flow in the sense that we mean the word flow. They certainly can't undergo any kind of change of state, an ordinary change of state as we understand that. All those properties of the liquid form, the material, are properties of the collective. You take 10 to the 24, whatever it is, H2O molecules in this bottle, and you get those properties just by massing them together. So maybe that intuition carries over to space. The atoms of space, the quanta of space, whatever, the strings, loops, et cetera, are not themselves spatial. Space is something that emerges in the collective. It's an emergent property of gazillions of those quanta. And the space we inhabit may be like a crystalline phase. It may be one of the many phases of that system. So that actually ties into the idea of locality again. So in a crystal, each part of the crystal has a well-defined neighborhood. So a given molecule or atom or whatever in the crystal has some neighbors to it. But that's not the case with the gas. The neighborhoods are always shifting around with that. There's no fixed sense of neighborhood. So our space is sort of like a crystal in some ways. It has well-defined neighborhoods of things. But you could melt space, evaporate space, screw around with space in different ways and transform it into different phases. And that would, independent of the kinds of phenomena I'm talking about today, that would actually be great to explain black holes. The black hole actually may be a place where space is literally evaporated. It's undergone a change of phase. In other words, in that case, there wouldn't actually be an interior to the black hole. The black hole surface would actually mark the end of space, and inside would be sort of like a vapor phase or something, but something that's certainly not spatial. I don't know if anyone here has heard of the firewall paradox that's been discussed in physics a lot, but that's kind of the outcome of that paradox, is to suggest that there is no interior of a black hole. So here's an animation that I created to try to get across in a very simplified model what I'm talking about here. So here we have a collection of 9 atoms of space. Those are the dots arrayed around the polygon. This is not a spatial system. This is meant to represent a highly energetic network. Each edge of the network represents a degree of energy, and every node is connected to every other node. So there's no sense of distance in this network. Everything is equally distant from one another. You couldn't even actually put that into I guess you need a 9-dimensional or 8-dimensional space or whatever to actually represent that spatially. So it's not a spatial system. Then you imagine cooling down the network, which corresponds to fewer links. And now you see what kind of network that you have. And somewhat contrived, but this gives you an idea of it. Now you have something that is beginning to look like space. There's a sense of, in other words, a sense of distance in this network now. You can actually assign coordinates and define a metric on this network. Now what's nice about this kind of thing is you can begin to play games. And you say, well, crystals have defects in them. They have irregularities, breakages and irregularity. Well, maybe we can try to think about what that would mean here. So in that case, maybe you maintain one of the edges. Here. It didn't in the process of cooling down go away. Now look what happens. You get a direct connection between this bottom left and the top right node in this little miniature, almost like Cartesian-like grid. That is sort of like having a non-local connection, because those 2 points in space, which on the face of it seem far apart, are actually directly connected. Sort of like a little wormhole between them. And actually there's a connection there with the idea of wormholes. So this is obviously a simplified model, is highly speculative, but I think it's fair to say, and I think it's defensible, I'd actually stand up in front of Brian Greene and Lisa Moon and the others and say, ha, you guys all think that space is constructed in some way or other. It's coming out of something deeper, be it just kind of graph theory approach or some other approach as well. So in that case, non-locality is no longer an insoluble puzzle. It's no longer supernatural. You can make it natural. You can explain it in terms of some kind of network. You have to expand your physical framework, but you can do that. More metaphorically, you can think of the non-locality as like the property of a Turkish rug. If you go to a Turkish or Persian carpet dealer, sit and have mint tea for a long time, eventually walk out with a rug or a kilim, and you can begin to look at the quality of the weave. You can look for worn spots, imperfections. I've got one at home. We've got one. I actually didn't want to buy it because it had this kind of guy. They drew a picture of a guy on it, and he didn't have an arm. And he looked like that. And my wife was like, George, no way. That's the cool thing about this kilim is that it indicates it was hand woven. There's a slight imperfection in the carpet telling you how it was made. So non-locality is sort of like that. It's an imperfection in space telling you a little bit maybe how space is woven. So let me just wrap up, and then I'd love to take your questions and talk about it more. You've got this phenomena of non-locality, spooky connections between different places, different things that by rights shouldn't be connected. And again, most of the time that would kind of be the end of the story, but really in the past 10 years, you're beginning to see, as people talk more about emergent space-time, germ of an explanation for it. It's derived from some kind of deeper structure in nature. And what's cool, and I hope science fiction writers will pick up on this, you can imagine universes that are not spatial, that the atoms have rearranged themselves into some non-spatialness. And anyway, what does that even mean? It's like, how do you visualize that? It doesn't mean the universe has gone away, but it's entered this other phase, and how cool would that be to try to visualize? Thank you very much for listening, and I'd love to take your questions. So I've been told that there's microphones, but I guess you guys know the routine much better than I do. Or we can talk afterwards outside.
I'm going way back over here to the start of the talk.
Sure.
My mind is totally now
Good.
Spinning around in circles.
That's where it should be.
But how do you actually measure when two photons strike at the same time? How do you actually measure things that are that close to one another in time and that are so small in terms of photons?
Good question. So the question is, how do you really know that you've conducted the experiment simultaneously on both wings?
Very small quantities of time, very small particles.
Right. So usually with that, actually, you kind of guarantee that by the path length in the experiment. You just make sure that the photons are traveling the same distance, and there's a variety of ways you can kind of test that and measure. You look for the phasing of the light through it. So there's a whole precursor to the experiment that will establish that the photons are traveling at the same, over the same period of time to each other. Does that answer your question?
Or like 20th of a second or something, like these things happen at the exact same time, 0.000, something.
Right. So there's some kind of master signal that's going out, and you have to be careful because things are happening at the speed of light here, that the distance over which the signal, that's provoking the two wings of the experiment to release their photons, for example, that the signal's traveling the same length, so therefore it takes the same amount of time, and that makes these two events, in theory, simultaneous. Now, obviously, there's going to be some kind of experimental precision on that. I think the limit is something like 10,000 times faster than the speed of light. That would be the speed at which something would have to cross the wing, given the precision of the timing on those experiments. I mean, you can synchronize them certainly with picoseconds or something like that, but I don't know what the detail would be. And then other fun thing you can do is because the Earth is rotating, you can actually watch the experiment for a 24-hour period. And if the universe has any kind of hypothetical frame of reference, that's an absolute frame of reference, you would rotate through that frame, so you should see variations in the timing, which you don't. So the whole thing seems to be kosher as far as Einstein's theory is concerned.
Okay, thanks.
Sure. It's actually fun to get into the nitty-gritty of these experiments. The timing is a huge issue. Those crystals are actually extremely inefficient. They'll release only like one laser photon in a billion will actually produce the entangled photons. So there's a lot of statistics that you have to work through on that. And that's why this has taken decades really to bring to its current state.
You skipped over some slides about holographic
Yes.
theory and how it relates to black holes, which is an idea I've learned about recently and is
Cool.
really compelling. So I was wondering if you could elaborate on how that might relate to non-locality.
Yes. So this might be too long for an answer to your question. We can talk about it more in the corridor. But it kind of goes back to what I was saying about black holes being like incinerators. They have a temperature to them. That comes out of the work of Stephen Hawking. So first of all, that immediately implies, by the way, that the black hole must consist of some kind of microscopic structure. Anything that has a temperature and can raise or lower temperature, like water, has to be molecular, because the molecular motions are what's actually storing the heat. It's what's actually representing the concept of temperature here. So the black hole already, has to be divisible into some kind of molecular, atomic, or microscopic structure. And then you can play other games. You can do things like hypothetical games of, well, if I add a certain amount of energy to, well, let's take it with water. If I add a certain amount of heat energy to this water, and the temperature bumps up just a teeny amount, then I know there must be a lot of molecules, because the energy is being divided over those molecules. If it goes up a huge amount, few molecules. You can actually count the number of molecules in the water that way. And you can do the same for black holes. And with water, when you do a counting exercise like that, the number of molecules is proportional to the volume of the water. If I have a bigger bottle, more molecules. It just scales up. There's a volumetric scaling. I still want to go back to the slide on this, but if you do the same thing for black holes, it scales up with the area of the black hole. If you do this kind of exercise of how many molecules does the black hole have, it's proportional to the surface area of the black hole, not to the interior volume. So black hole from the outside looks three-dimensional, but it's behaving as a two-dimensional system. And that is where the word hologram enters this whole discussion. Because a hologram, Princess Leia, looks three-dimensional. You can actually walk around the droid projecting Princess Leia and see it looks three-dimensional, but you know that it's a two-dimensional, ultimately two-dimensional. And you could probably get that by looking at the kind of details that Princess Leia had. If you enlarged the hologram, you begin to see some graininess in it that would indicate the thing is actually a two-dimensional projection.
But isn't the surface area of the black hole related to its volume, like a sphere?
You would think so, but no. There's a couple levels at which the answer is no. First, the level is actually, even in general relativity theory, the interior of a black hole is a highly distorted space-time. So it doesn't scale up. There's actually kind of more space in it than there should be, in a way, because of this distortion. So it looks like a ball on the outside, but you can't do Euro 4/3 pi r cubed with it. It doesn't work like that. And worse, in the quantum theory of gravity, at least according to some of these interpretations, there is no interior. So there's nothing to volume. There's no volume there at all. So, but the connection to locality, I promised to go back. The volumetric scaling is actually related to locality. So if you scale up, if I have two water molecules certainly, but certainly bottles, I can kind of treat each independently and then add up the total volume, because I've kind of divided the bucket of water or whatever I have into subvolumes and added up the subvolumes to get the total volume. That's where you get the volumetric scaling. You just integrate over x cubed. So that volumetric scaling is failing for black holes. And since the volumetric scaling comes out of locality, it means locality is failing for black holes. A lot of these black hole arguments require a couple stages in the logic.
Thanks.
Sure. So you guys are all happy with all this and there's no questions? And it takes time to formulate them, so I think I'll be around for lunch and you're welcome to kind of pester me.
I just have
Sure.
One question. I didn't understand well, by some definition of understanding, the part about when you're saying that the black hole is irreversible, you're saying that you would expect it to be reversible, but it's not. But I didn't quite understand. You would expect it based on what? Based on the way the math works out? And
Yes.
The other one based on observation? And it's
Yeah,
not clear why
I rushed through that, and I'm glad you called me on it. So the question is, in general relativity theory, black holes are irreversible by definition. You fall in, you can't get back out. It's all the well-known properties of black holes. You'd have to exceed the speed of light to get out specifically. So that has always been considered a paradox in a way. It's always been considered a problem that black holes seem to be irreversible when everything else in science is.
And by seem to be, you mean seem according
Yes.
to the math?
Yes.
Or
Yes. Well, certainly according to the theory, they're observationally irreversible. What's a good example of that? I mean, the simple example would, and it's not entirely the same as the theoretical one, but I'll give it to you anyway. So if you have a neutron star, just any physical object, and matter falls onto that object, it will heat it up. It's like if you pummel it, it will heat up, and the object will radiate away that energy. So there's a steady state that will be achieved in any kind of material system, and this is a well-known aspect of stars and other systems like this. Black holes are unable to achieve any kind of steady state like that, at least according to the theory, and also according to observation. So if you see in the example I showed, the black hole was actually sucking in some gas, but it wasn't, as it sucked in, it didn't heat up and release the energy of the gas out again. So there seemed to be an irreversibility in that process. So the contention that Hawking made is that if you look long enough, as in 10 to the 30 year long enough, you would eventually see the energy merge back out in the form of these Hawking particles. And that also was irreversible because the Hawking particles coming out are random. You couldn't unwind the system.
They're not correlated with what physics.
Exactly. There's no correlation. In fact, I'm glad you bring up the word correlation there, because if you had two entangled, if you play the game, two entangled particles, you threw one into a black hole, the one that came out would no longer be entangled with that one that you kept, which is violating the kind of violating the reversibility of quantum theory. That's actually why it's called a paradox, because quantum theory is telling you that you have an irreversible process which is against quantum theory. So there's kind of a loop there that it's contradictory. Does that help any? I know it's
Yeah,
kind of hard to get your mind around, but
thanks.
sure. Well, thank you all for coming today. If you do have questions, pester me. I'm happy to, and I actually, for me, the benefit of giving these talks is really the questions, because they provoke me like I did with the down conversion crystal. I actually modified the talk, and we'll modify another edition of the book based on the questions that I got. So if you do have questions, feel free. Or if you don't want to ask them, I can give you my email address later and we can talk. Thanks.